Okay, so today is our third and final lecture on functions. This lecture is important for the tidyverse, and other than that, it's not really important. So if you want to program with the tidyverse, then that's the main thing we're going to be focusing on here, because what makes the tidyverse easy to work with interactively is also what makes it difficult to program with. And so we'll talk about some ways around that. But actually, before we get to that topic, we're going to talk about sort of best practices in writing functions and things you should think about as you're writing functions. Okay, so this is the agenda. We're going to start with what makes a function good, right? And as I kind of mentioned last time, functions, the best function is a function that works, right? And then the worst functions are functions that give you wrong output. And then there's a whole bunch of in between there, right? So just because a function works doesn't mean it couldn't also be improved. And if it works for you for one situation, that doesn't necessarily mean it works for all situations always, right? And I promise if you have a lot of people that are using your functions, you will find that they use them in unexpected ways, and that leads to errors. So, so we'll talk about sort of best practices that way, and then we'll talk about building up functions. So I think one of the things that is surprising to people a lot of the time is they think about functions as being these super complex things. And really, best practice, an individual function should be small. Every function should ideally be small, like less than 50 lines of code. If you're getting beyond that, then it's probably an overly complicated function, okay? R also is sort of notorious for having people who are really good at quantitative work, but not very good programmers. So you will find in many packages functions that are 1,000 lines long, one function that's 1,000 lines long, right? And that's less than ideal for a couple of reasons, but the main reason is because it makes debugging harder. So when you do run into an error, it says the error is in this function somewhere, and that function is 1,000 lines long. So then you've got to sort through the whole thing. Better practice is to build up functions. So you write one function to do one thing, and then you write a different function to do a different thing, and you write a third function to do a different thing, and then your final function calls all three of those functions. Okay, so if you took all of the code from each of those 4 functions and put them all together, it might be, say, 100 lines of code. But each of those functions is only like 20 lines of code or whatever, right? So that's sort of the idea. Then at the end, and this will actually be a big part of the lecture today, we will talk about non-standard evaluation, which is the tidyverse training stuff I was mentioning. Or not training, tidyverse function stuff. Okay, so primary learning objectives: understand how functions build on top of each other and why only do one thing is a good mantra for a function. And then understand what non-standard evaluation is at a high level, okay, even if you aren't able to fully work with it. So my hope is that you will be able to sort of use this newer syntax. It's like maybe 2 years old at this point, so I guess it's not that new, but to work with basic problems with, say, dplyr, if you wanted to write a function with dplyr. But I'm not expecting, even though we will go into it some, I'm not expecting that you'll have like a deep understanding of non-standard evaluation at the end and that you'll totally understand it, okay? So I'm trying to give you sort of a high-level overview and then use cases for you, all right? But don't worry if some of it's really confusing. All right, so what we're gonna do now is maybe I'll just put you in breakout groups and we will talk for just like 2, maybe 3 minutes about what you think makes a function good or bad, okay? Okay, so somebody unmute, please, and tell me some of the things that you talked about.
Meaningful error messages.
Good. So if there is an error, hopefully that error will spit out a message that tells you where the error is coming from. So the input was expecting it to be numeric and you gave it a string or something like that, right? I will say too, though, that sometimes people just do not read error messages. So that's problematic also. Other ideas, thoughts?
It doesn't use names of other functions and other packages.
Good. So a very common use or a common example of that is the mass function or mass library, which comes with base R actually. And when you load R, I think mass is loaded, I'm pretty sure. And it has a filter function. So when you load dplyr, it has a filter function. And so then you have a conflict there, right? And so because you're always loading dplyr after mass, hopefully, then that one works. But if you do it in the opposite order, then it'll be trying to get the mass function filter. Other thoughts? All right, so this is a little bit lower level than that, but how about correct output, right? We want what you're getting to be correct, right? That's a pretty important part of a function. Brock, do you want to say
an error message in time, like Joe said, a message that's meaningful, but one that happens in time. Like I can't do a whole bunch of stuff and then get an error message.
Yes, I don't know if you can hear him. But yeah, so basically the error message should come early, right? And you shouldn't get way down the line and then an error message comes. The other thing that Brock talked about when we were chatting is having output that is helpful. So you could have the correct output and it could be everything is great, but it returns it to you in some deeply nested list that's hard to work with, right? So that's technically not an error. It's not anything that's wrong, but if it returned instead like a data frame or a vector or something that's a lot easier to work with, then that would be more ideal, right? Okay, so this is when we're thinking about base R, right? Base R is very hesitant to ever change. And so there are problems with some functions that have existed forever. And I will say, within just the last year or so, they have finally started to become a little more open to changing. But the reason is because, so I'm talking more about this bottom part right here. The reason is because they want to make sure that the code that you write in 2005 will still work today in 2021. And fairly amazingly, it does, right? If you're using the most current version of R and you're running code that you wrote 15 years ago or more, it will still work. And that's pretty impressive, but that leads to this very conservative view of once a function is released, it doesn't get updated, even if there's problems with it. Okay, if there's like outright errors, then okay, we will change it. But generally, they won't change it for any other reason. Okay, the tidyverse tends to be, so this is where base R is, right? The tidyverse tends to try to be more here, where it's like, okay, here's a function, and we're going to put it out there for a while and see how it works. And then people are going to run into hiccups about it. And then we're going to continue to change and modify those functions over time to make sure that they are as user-friendly as possible and that they all work in ways that sort of make intuitive sense. So that's more of like a utopian view where it's like everything just flows together and it works really nicely. The problem with that approach, of course, is that if you have functions that have been fully deprecated, then your code from 5 years ago may not work anymore. I will also say, though, that the tidyverse has changed in that a lot, and it's almost impossible for that to happen anymore. They have this whole licensing system that they're using with, or not licensing, I can't remember what they call it, but they have this whole badging system. And so if you get a chance, you can still see Hadley's keynote from the last RStudio Conf, where he talks about that and how they make sure that code is still going to be working later down the line. But this is more where the tidyverse tends to stand, whereas base R is more down here. Okay, but R sort of as a whole, generally, right, has this tension as well, where there's full-on programming that you want to do. So you want to write a program to do something. And then there's this part, which is this interactive exploration part, right? So you get some data, you want to load it in, and you want to explore that data, all right? And you want to be able to do it interactively. So this, like, fully over on this side, like if we went all the way over there, would be something like maybe, I don't know, like SPSS or whatever, where it's not really programming at all. It's just you're working interactively with the data, right? And so base R tends to be somewhere about here. So it is a programming language for sure, but it's really built for interactive exploration. And so then there's things that you can do later where you're implementing or you're getting it to work with like C and things like that. But C is a good example, right? The language C, it's far more like here. It's not meant for interactive exploration at all. It's meant for writing programs, okay? So then this part, this tension between interactive exploration and programming ends up being sort of a challenge as well, okay? So when we're writing functions, there's sort of, there's a bunch of different ways that we can do this, right? But this is sort of the worst case, well, not the worst case scenario, but this is not a good scenario, right? You have some bad input, it goes to this first function, which then passes to the next function, which then passes to the next function, and then finally you end up with some uninformative error, okay? And this is happening because whatever the bad input is here, it can still run its stuff. It just gives a different kind of output that it's not, that it wouldn't necessarily expect. This one can do the same thing. And then finally down here, now you end up with something where it's trying to compute a mean of a, character vector or something. And then it's like, blah, 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 blah. It says some base R error message that makes no sense because it's related to something that's going on in this function with some output that was generated from this function with some output that was generated from this function from the bad input. Okay, so much better then is to have these catch points, right? So this same sort of function line could be here where you have bad input and then you immediately get a useful error. So again, just like super simple example, it's expecting numeric and it's actually character. You could have it check that right here. And then if it isn't of the type it's expecting, then it will tell you that specifically, okay? So you will always have error messages, but those error messages are often generated by other functions you're using and not your functions, and that's less than ideal, okay? Chris.
I have a question about I guess this is more on the last slide than this one, but if you're doing something like developing a package, and you want it to be running in the long term, there are some other languages that do virtual environments where you can pull an environment that has all of your packages with specific versions. So it doesn't matter if you do this 15 years from now because it's using this one specific version and it works. Is anyone doing things, or is it bad practice in R? Because you said if you change the global environment, that's bad, where you would have them install from GitHub the version that you made it in, and so it works 100%, and then the code runs, or is that bad practice?
Yeah, so for a package, you would not do that. There is a function, or there's a package called renv, R-E-N-V, and it's a super great package for doing exactly what you're talking about, where you basically take a snapshot of all the packages you're using, and it gets exactly the same version of all of those things. And then if I wanted to share it with you, you would download from GitHub, right? You would clone the repo, and then you could just run snapshot refresh or whatever, and it would go and grab all of those packages at that same version. But in package development, you would not do that, because you want, very rarely there are times when your package needs to depend on a specific version of a previous package. But the vast majority of the time, you want your package to be working with the most up-to-date versions of those other packages. And partly it's because you're not going to, when people install your package, you're going to either have them install those dependencies, or you're just going to assume that they have them. So for instance, if they have dplyr and ggplot and tibble and your and tidyr, say, and your package depends on all of those, you don't want them to have to go and reinstall old versions of all of those things just to get your package to work, right? So so with packages, you would generally not do that, but for a research project, you would, and Ren is a great way to do that.
Thanks.
Yep. Other questions? Okay. This is sort of just like a continuum that these past 3 slides I said are all from Hadley's, one of Hadley's trainings. The sort of best case scenario is that you get the right answer, right? And as I mentioned before, how you go about doing that is fine, right? It doesn't matter. If you get the right answer, you get the right answer. Great. But there's also always, just about always, room for improvement too. So that's kind of thinking through those things. If it does the right thing, you get the right answer, great, right? You can stop from there. But if other people are going to be using it, there still might be reasons you want to refine that function, even if it's giving the same answer, okay? The next best case scenario is that you get a useful error message. So the function doesn't work, but you at least get a useful error message telling you why it's not working. Then after that would be a not useful error message, and finally the worst would be the wrong answer. And specifically, the worst is when you get a wrong answer and it's silent, right? So you don't get a warning, you don't get an error message, and you get the wrong answer. That is way less than ideal, right? So what does this mean operationally? It means a couple of things. One, I've sort of mentioned this a couple times already, but your functions should do one thing and they should do it well, okay? So you should always be trying to write your functions so they're doing one thing. So for example, let's say you have the final function that you want to produce is something that produces some plot, okay? To do that, you're probably going to have to assume some data structure. You also might have to do something like compute means and standard deviations or some other statistic, right? So what you would do in that case is not write one function that brings in the data, that transforms it, that computes the summary statistics, and then produces the plot, right? Instead, you would write one function that maybe brings in the data or whatever, like let's say it's the data are online. Maybe there's a function to do that. Maybe there's a second function then that transforms the data and makes it ready to go. That then feeds into a third function where you compute all the statistics that you need for the plot. And then finally, the fourth function would be the one that actually produces the plot. Okay, so each of those functions flow into each other, and you'd have probably finally a fifth function that calls each of those 4 previous functions to actually produce the plot. Okay. So the other thing I would say is be careful about naming functions. So ideally, you want to be as clear as possible. And this is one area where I think the tidyverse does a really good job, right? So because the tidyverse is focused around verbs, and one of the things that they have done that I think is really helpful is not only do they do that, but they have talked about why they do this, and it has sort of proliferated throughout the community. So now lots of package developers, including myself, try to write functions with names that are verbs, like what is this thing doing, okay? And it's not easy. It's very often it's harder than you would expect to create a name of a function that is very intuitive, right? So for example, even like filter, right? Many people want to use that for columns rather than rows. And so that's like hard, right? But like pivot longer is another example where that used to be called gather, and that function actually still exists, but that wasn't as clear to people. So in the sort of updating of that function, Hadley initially called it pivot, but then, or pivot long, I think is what it was. And then he asked for feedback from the community and then settled on finally pivot longer, because it can always be longer, longer, longer. So not pivot long as in that's one thing, but pivot longer, right? Ideally, you would embed useful error messages and warnings. Again, as I've mentioned a couple of times, a lot of this is kind of for like more package development sort of stuff, or just other people are using your functions. I almost never embed errors or warnings if they're just functions that I'm using at one point in time. I'm not saying that you shouldn't, but just generally it's not as important. If you know you're going to be coming back to that function later for something else, then I would for sure do that though, okay? And then the last point is sort of the same idea that I've mentioned already, where just because your function is working doesn't mean it can't be improved. And that's what refactoring means, okay? So refactoring your code means you're going to go into a function and the output, the behavior of the function is not going to change one iota, right? So from, say, the user end, they run the function today and it gets the results that they want. You do a bunch of refactoring, they run that same exact code 2 weeks from now, and it still works exactly the same, but the internals of it are different, okay? And so why would you do that? There's a bunch of different reasons. One is to make the code more readable. Another is to make it faster, right? And another would be to make debugging easier. But there's other reasons as well, but those are probably the main reasons. Okay, so here's an example. This is a function that we wrote last week. Okay, so this was that function where we're taking two numeric inputs, and we're trying to look through those vectors to see where it is NA in both elements. Okay, so let me go back here. So this is like the vector, right? So it would say false, false, true, false, 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 true. And then we're just going to sum the trues. So that would give us 2. Okay, so what we did in this is we first said, okay, is the length of x equal to the length of y? Okay, and in this case, I'm saying, is the length of x not equal to the length of y, right? And then if that is true, so the lengths of those two things are not the same, then it goes into this part, okay, which comes down to here. And if it is true, then it's just gonna skip that, and it's gonna go to here, right? Because this goes with that. Okay, so if it's not true, then it's going to first calculate the length of x, calculate the length of y, and then I'm creating this thing here that I'm calling v lengths, okay, where I'm pasting together x is equal to the length of x, y is equal to the length of y. And then that just goes into a warning message. So if the length of x, %%, remember this is that modulo operator, so it gives us the remainder. So this is the way to just check that they are, like, if one is 4 and one is 2, then they are recycled, right? And so if it's recycled, we want to give it a warning message, and otherwise we want to give an error message. Okay, so this checks if there's a remainder of the division between these two things. So this is checking, this is actually calculating the remainder, and then we're saying, is that equal to 0? So this is saying there's no remainder when I divide x by y, or there's no remainder when I divide y by x. Okay, if those are 0, then we go into this warning and we say vectors were recycled, and we paste this message here. Okay, otherwise we say stop, vectors are of different lengths and are not recyclable, and then we state those vector lengths again. Okay, So all of this is just like checking stuff that we're doing, okay? And then after that, we're going to do this. So we're either going to get this warning, and then it's going to do this, or it's going to do nothing in this spot, and then we're going to do this, or we're going to get an error if they're not recyclable. Okay? So this is a fairly complicated function at this point, even though the actual operation that we're doing is not very complicated, right? So if we're looking at this, though, can you think of anything that we could do to clean this up, to make this code better? Even though it's doing what we want it to do right now, it can always be improved. Can you see anything that you think right away we could do that to make it easier to read or whatever?
Spit out some lengths if there are different lengths.
So it's actually doing that already because it's creating this message here where it's length of x and length of y, and then x is equal to the length of x, y is equal to the length of y. So I have to scroll over here a little bit, but see this v length
Okay.
pasted in there. Any other ideas? Okay, well, one thing we could do is we could create a different function that just calculates if they're recyclable, if two vectors are recyclable. So here, we're kind of doing that here, right? And we have this is kind of weird. So instead, I'm just going to create a function that's recyclable. And what I would actually probably call this now is underscore recyclable. Is it recyclable, right? Are they, or are recyclable? That seems weird though. Okay, so what this is going to do is we have two generic vectors, x and y, and we have test1 and test2. And then I'm just saying if any of those equals 0, then we're good. So is one recyclable to the other, or is the other recyclable to the other, right? Are they recyclable in either direction? And if yes, then it's going to return true. If not, then it's going to return false. Okay? So now I have this function. I can use that. Well, first I want to test this function, right? So generally, anytime you're writing a function, you want to do at least these informal tests. Later, we can talk about, we'll talk a little bit about more formalized tests, but we won't talk about it too much. All right, but here's two vectors, A and B, and I can call this recyclable on it. And here I'm saying recyclable A, B, and it says true. Well, they're recyclable because they're the same length, right? Then on this one, I say A and BB, and I get true, right? A and BBB, I get true. But if I say AA and BBB, then I get false. Okay, so now I can use this function within the function that I just used, and that would look like this. Okay, so here's my function xy. If not recyclable, xy, then stop. Okay. If the length of x equals the length of y, then just return the thing we've already done. And then we could say else, but I'll just make it more explicit here. If recyclable, x and y, then warning. Okay, and then also return this sum. So that makes it a little bit more readable. But is there anything else we can do now? Well, first we can test it to make sure it's working. Both NA for AB, we get 2. Both NA for A and BB, we get a warning, but we get 4. And notice it gives us our lengths, 7 and 14. Both NA, AB, BBB, error, vectors have different lengths, right? And then both NA, AA, and B, warning, but we get the output. Okay, so this is working, so that's cool. So that's an example of refactoring, right? The code itself, the function itself rather, is not doing anything different than it did before, but the internals of it are a little bit different. Okay, anything else? One thing we could do is we could actually make the errors and the warnings a function themselves. So we could create a function which I'm calling check lengths. Okay, So we have a function xy. We say if not length of x equal length of y, then it's going to go into here. So it's just checking first to see if the lengths are equal. Okay. If the lengths are equal, we could have had not equal there too. That'd probably be easier. I don't know why I did it this way, but if the lengths are equal, notice this here goes to here. So it's just going to return nothing if the lengths are equal. Okay. And if they're not equal, then it will go into here. And it's first going to say, okay, are they recyclable? And if that's true, it'll spit a warning. Otherwise, it will throw an error. Okay. So it's checking if they're the same length. If they are, then it's checking if they're recyclable, or if they are not, then it's checking if they're recyclable. If they are recyclable, then it gives a warning. Otherwise, it gives an error. And if they are the same length, then it's just going to exit and you'll get null. Okay. So now our entire function looks like this. Okay. We have both NA, function XY. We check the lengths, and then we sum like we had before. Okay. So in terms of readability, this function is much, much better now, right? It's really small, and it's very clear what's happening. We're feeding it an X and a Y vector, and the first thing we're doing is checking the lengths of those vectors. That's going to return a warning or an error or nothing, right? And then we're going to do the body of our function. The reason we can just do it like this is because if this returns an error, it will exit the function there. Okay. So it won't go on to do this or to try this. Okay. So we can test it again. We get 2, warning, error, warning. Okay. So the output is again exactly identical, but we've refactored the code. So we're now actually using 3 functions, and then the body of that main function is very simple. Okay. Questions on that? Does that make sense why you would want to do that? Okay. So as this is sort of a reiteration, but we would want to do this to make code a little bit more readable. We also, if we're writing many functions, there might be cases where we want to actually reuse these recyclable and check lengths functions, right? Depending on what we're doing, these functions might be helpful across a bunch of different functions. Okay, so in addition to sort of making one function a little bit more readable and easier to kind of understand what's going on, we might save ourselves some work by being able to reuse those functions later. And then it can, although in this case it probably didn't, but it can make debugging easier because of having that early exit and having useful error messages. Okay. So this is a quick example on debugging, since that last one wasn't a great example. But here, this is like, a little bit hard to kind of understand what's going on, I think, but we'll walk through it. Okay, so I have this function here, which is called f, and it takes an argument a. Okay, this function f calls a different function g, which gives the argument a to g. Okay, g is a function itself, which calls the function h. Okay, and then h is a function that calls the function I. And finally, I is a function that does this. It says, if not numeric, stop, d must be numeric, call.false, and then d plus 10. Okay, so it's going to add 10 to whatever the input is here. Okay. So if I say fa, then I'll get an error, right? But then it will, if I want to debug that, I can use this function traceback. Okay, traceback will look at the stack of functions that were called and tell you where the error actually occurred. Okay, so I called f of a, that called g of a, that called h, which called I, and finally we get stop there. Okay, and if we go back here, you can see I is where the error actually occurred. Okay, so this is obviously a you know, not a real example. It's just an example to show you how the full call stack can be displayed when you're using traceback, which is a good way to debug your functions. Okay, so again, if f was like this big complicated function, then I fed it some unexpected input, it would say, I could do traceback and it would say f. That was where the error occurred, right? Whereas if I have a bunch of other functions that it's calling, it will take f and then go into there. And actually, fairly regularly, even when you're calling other functions like this, right? And let's say you miss one of the checks that you should have done, so then it keeps going further than you would ideally like it to be, and you get some weird, crazy error message that doesn't make any sense. That's going to be because as you're going through the call stack like this, you'll see like, oh, I called this function, which then called mean, which didn't have na.rm equals true in it. So then that fed an na to this other function and blah, 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 right? So using traceback can really help also. Okay, so that's sort of it for this section. Are there any questions before we move on?
Why is there a dot after the call?
So when you do, that's the argument. I don't know why it's called that, but if you do call dot and then say false, the default is true. If you have it as true, then it will say error in I, and then it will say your message. Otherwise, it will just say D must be numeric. So it's just a different way of displaying your actual error message. Okay, moving on to non-standard evaluation. Okay, so this is just a note to say, were it not for the tidyverse, I wouldn't even cover this topic. I don't think it's incredibly important generally, but it is important if you're going to be programming with the tidyverse. So I'm going to give you an idea of what it is, and then we're going to dive kind of deep into the weeds on that, where it's going to feel like really uncomfortable. Okay, and then we're going to pull back from there, and I'm going to give you specific examples of how you can use it. Okay, so non-standard evaluation is basically just an implementation of different scoping rules. So in dplyr and lots of other ones, the arguments are evaluated inside data frames rather than the current environment. Okay, whatever the current environment is. So we do this by capturing the arguments that are supplied and then sort of pulling them to where we want them to be evaluated and then evaluating them there. Okay, so normally, for example, if I just said X, it would go to the global environment and try to find something called X, right? But that's not generally what I want when I'm in dplyr or whatever, right? I want it to look for X inside df, whatever the data frame is that I passed it, okay? And so that's hard, right? That's not a normal thing for R to do. That is, so lexical scoping is what we talked about before, where it's going to look inside the function, then it's going to look to the next sort of layer and the next layer. But this is different from that. It's going to say, don't do that. Instead, just capture that argument, pull it over here, and then evaluate it within this environment. Okay? So this is an example using sort of the base methods, where we're using that %df function that we created the other day. Okay? So here is a function x, and the first thing we're going to do is we're going to sort x. Okay? Then we're going to put it in a data frame where I'm going to have the sorted version of x here, and then the percentile, which is going to be equal to the empirical cumulative distribution function, whatever. This doesn't matter. It's just the way that the percentile is being calculated. Okay. Then I want to change the names for this first one to be equal to the argument that I supplied. Okay. And this is actually a good thing to do because then that helps your output for your users. So they're like, oh, okay, so I know that's the thing I gave it or whatever. Okay, so what it's going to do is it's going to capture the output or capture the input here, and it's going to replace it here. So to do that, we use this function substitute. Okay, so x is the argument for the function, but whatever you give x, it's going to substitute that in for x there. Okay, so then we get the names of d is equal to the substitute version of x. And I'm just going to paste 0 that thing and collapse it with an underscore. So if we have spaces or whatever, it'll end up like that. So then I say percentile df, and I just say r norm with some arguments. And then you can see the name of that first column is equal to this thing, right? It's equal to the thing that I feed it. Okay. And that's happening through that substitute call. Okay. Confusingly, though, substitute works differently inside a function than it does outside of a function. So if you're using it outside of a function, it works just like the function quote. It quotes the input. Okay. If you use it inside a function, then it does what the name implies. It substitutes the input for what you supplied. Okay, so here's an example. If I say quote, and then I give it something, it just gives me that back. Okay, so it's not evaluating anything. It's not actually trying to do that operation. It's just quoting what's inside of those parentheses and giving me that back. Substitute does this exact same thing if we're working outside of a function. Okay, but if we're working inside of a function, so here I'm creating a function called extract var, and it's a function that takes this df and var. If I say substitute df and then I say extract var empty cars, then it gives me empty cars in return. It doesn't give me df. Okay? Does that sort of make sense? So if we want to actually get this thing to work, we generally need to do more than quoting the input. Okay, so here now I'm extending this. So I'm saying subset, and I'm going to say eval, meaning evaluate the input that is supplied here. Okay, and then select whatever the variable is. So now with extract var, I can say extract var empty cars, and I can give it empty cars as this bare variable like that, and it will go into here and evaluate it there within this subset function rather than looking at the global environment. Okay, normally when you normally write R functions, you cannot pass bare variable names like this because it's going to look in the global environment for those variables. Okay, empty cars does exist in the global environment, but it's not looking there for it. It's just quoting the input, basically. It's substituting that in for df, and then it's going to evaluate it there instead of outside. Okay, so substitute is quoting the input, but then we need to evaluate it. All right, and so all of this is confusing, right? And this is why I said I wouldn't normally cover this, except it's used everywhere in the tidyverse, right? This is why you don't have to use the $ when you're referring to variable names, which actually itself is a form of non-standard evaluation. You don't have to use quotes for everything, right? So everything just works. You just give it bare variable names and it all just works. And that's because of this non-standard evaluation, okay? And it's used so prolifically throughout the tidyverse that they implemented their own version, which is called tidy_eval. Okay, we'll get to that in a minute. We're not going to go very deep into it, though. It's a really complicated topic, and there's a whole lot there. Okay, but if you do start to program a lot with the tidyverse, you'll probably need to at least dip your toes into those waters. Okay, so here's an alternative version. Okay, where I'm saying, thank you, where I'm saying extract the var, and I want to be able to give it the data frame and the variable with both just bare names. Okay, So what I'm doing here is I'm saying eval substitute var, where the environment is going to be df. Okay, so what's happening here is this substitute is just going to pull whatever the name is of the variable that I'm giving it, and that is going to be a string. Okay, when it substitutes it, then I'm saying evaluate that variable within inside the df environment inside of here. Okay, so now I can say extract var empty cars mpg, and it pulls the mpg column from there with me just being able to supply the bare variable names. Okay, so this is good. This is equivalent to df $var, but it's sort of nicer because now we can work with it programmatically. We can swap in different data frames and swap in different variables, and it should all just work. This is maybe a little bit more simple in terms of thinking about how we subset things the way we normally do. So we have the data frame, and then we're going to say, give me this column, right? And I'm just saying as.character on that substitute, and then it gives me the same thing. So if I don't wrap it in as.character, it's actually technically going to be a symbol, which won't work. So we could, but this is kind of nice too. We could also add like drop equals false if we wanted to, and then it would return the data frame structure still. Okay. The last thing that we could do here, this is now basically replicating dplyr select. We could say function, and then we say, instead of having a specific variable, we just give it the dots. Okay. And then the dots could be one variable, it could be two variables, it could be 76 variables, right? It could be anything. And so we have to wrap that in a list, but we're wrapping it in a specific kind of list called a list, which is like basically it's going to capture everything, but it's not going to do anything with it. All right. And then we're going to substitute everything in that a list. And then we just do this exactly like we did before. The only thing I'm dropping -1 here because the first element in when I call as.character on vars is going to be a list. Okay. So a list is this, and that's going to be part of that character vector. So I drop that, and then the rest of it is just, this is going to end up being a character vector of the variables that I supply here. So I can say extract empty cars, mpg, sil, and disp, and we get a data frame like this. And notice I can get all the bare variable names. Okay. So this is fairly into the weeds at this point, right? And this is where I'm saying, like, if this isn't making total sense, that's okay. What I want is for you to get a general sense of why we can use bare variable names like this in the tidyverse, but we can't in most other functions. Okay, and it's because this kind of stuff is happening under the hood. All right, so it's used so frequently in the tidyverse because it makes working with these functions interactively easier. Okay, so we can just do mpg and select whatever, right? But it does make programming with them more difficult. Okay, so if we didn't use non-standard evaluation, this code wouldn't work because it wouldn't know where manufacturer is supposed to be coming from. It would probably be looking in your global environment for a variable named manufacturer, which doesn't exist, right? You want it to look within this MPG data frame. Okay, so moving on from that, let's talk about specifically working with dplyr to program. Okay, so let's say we wanted to write a function that returned means in a nice table-y format for a variable by two groups. Okay, so you want basically like a crosstab sort of thing. So typically, we're going to start by solving this problem for a single situation, for one small problem, and then we're going to take that code and we're going to generalize it to a function, right? So let's do it. 4 minutes, take this code and try to generalize it into a function. Okay, so this is, we're taking empty cars. So take it so it will take any data frame and then group by any two variables, and then compute the mean of that, of a third variable. And then it's going to pivot wider. So the names are from sil Okay, and the values are from mean that you're calculating here. So this is how it's going to look for this one. But ideally, you would want to swap out the two variables here and the third variable here. Okay, so this is hard, but give it a try. Maybe we won't take the full 4 minutes, but try to generalize that to a function. Okay, let's go ahead and stop there. Was anybody successful? Okay, that's what I would expect. And this is frustrating because it seems like it should be pretty straightforward, right? It seems like we should be able to do something like this, right? Here's the function. I'm calling it group means. We want to pass it the data, the outcome, the thing that we want to sort of summarize, and then group 1 and group 2, right? Then we're going to say data, group by group 1 and group 2, summarize where the mean is equal to the mean of the outcome, and then pivot wider so the names come from group 1 and the values come from mean. Right? This is the exact same thing we just had, but we've just generalized it to a function. But it doesn't work, right? And the reason is because it can't find those things. It doesn't know where group 1 or group 2 are, right? We pass it just like this, we would expect that to work, but it doesn't because it just doesn't know where to find those things. Okay, so it's looking for an object called group 1 that doesn't exist, right? We're feeding it MPG, and this is also an example where we have an error, and the error from the user side would make no sense at all, because it's like column group 1 is not found, column group 2 is not found. What are you talking about? I didn't give you anything called group 1 or group 2, right? Those are inside the function though, and it's looking for these variables inside the function. It can't find them there. So then it's looking outside the function at your global environment, and it can't find them there. So then it gives an error message saying it can't find those things. Okay. So instead, we need to quote it and evaluate it in the correct place. Okay. So this is one way to do it, and I'll show you a slightly easier way in a second, but I want to show you this way first, because this goes more along the lines of what we were talking about before. Okay, so first we have the data, we have the outcome, group 1, group 2. So all of this is just the same. But now for the output G1 and G2, the group 1, group 2, we're going to quote those things. Okay, and I'm quoting them using this function enquo, which is from tidy_eval. Okay, and enquo is to quote a function inside a function, or quote an argument inside a function. Okay, so this is going to take whatever you give as the outcome, it's going to basically substitute that. Okay, so this is essentially the same thing as substitute for all of these. It's going to take whatever you give it and substitute it for the argument name. Then down here, we use this exclamation, which is read bang, bang, on G1. Okay, so this G1 is now quoted up here, and we use that bang, bang to say now evaluate that thing here, right, in this group by, instead of outside of that. Like don't look anywhere within the function, don't look to the global environment, just evaluate that quoted input here. Okay, so bang bang G1, bang bang G2, bang bang out, and bang bang G1, and then now it all should work. Okay, so it's going to evaluate each of those quoted things up here in their correct place. Okay, so now when I call group means, it all works. Okay, and this is now a pretty nice function that we've created, right? But that non-standard evaluation makes this a much more difficult function to write than what we probably would have expected to work, which is that, right? That looks like what we've done in the past. That looks like how we would expect it to work, but it doesn't. So we have to do something like this. Okay, does this make sense sort of conceptually in terms of what's going on? Or are there questions that you have that we can maybe probe this a little more to figure out what's going on? Okay, so I'm going to show you an easier way to do this now, where we don't have to do all of this. It'll kind of do it for us, but this is what's going on in the background. Okay. So, well, first, I guess I have this one. This is not where I was expecting to go. Another option that we can do always is we can pass the dots just like we did before, but we don't have to worry about the A list or whatever. So here I'm saying pass the dots to group by. I still have to quote my output and then evaluate that there. But now it works like this. This is not quite the same thing because it doesn't do the pivot wider. But as a side benefit, you can now give it as many variables as you want and it will work. So that's nice, right? We're going to do price, but we're going to group by cut, clarity, and color, right? So cut, clarity, color, and there's the mean price. Okay. But this isn't the same thing. So passing the dots won't fully fix the problem. There is an alternative. I don't remember what this one is called, but this is the sort of newer, probably like 2 years now. So not real new, but I still think of it as new because it came out after the tidy eval one. What we can do is we can write the function basically the exact same way that we did before, but with one exception, which is that we're going to wrap each of those arguments that need to be quoted and evaluated. We're going to wrap them in these double curly braces. Okay, so group by group 1, group 2, outcome, group 1, all of those things that need to be quoted and then evaluated in the correct place, we just wrap them in these double curly braces. And then we don't have to worry about that in quo and the bang bang part, and it all works. Okay, so does that make sense? This is basically doing both of those operations at once. Okay, so this is, again, though, this is just an alternative syntax to do the same thing. So it is basically the same thing. So one thing that's nice here is because data is the first argument in our function is sort of tidyverse-esque, right? So we can do things like this: diamonds, filter, select, and then group means 3, and then it'll work, right? Because remember, always when we're piping, it's just piping whatever the output is from the previous thing into the first argument of the next function. And so if our first argument of our function is a data frame, then as long as we're piping a data frame through, then we can use our function just like that as we would in the tidyverse. Okay. All right. So the double curly brace syntax is quite a bit easier to apply, I would say, than using in quo and then the bang bang. It will get you out of tidy eval complications probably 80% of the time in my experience. Okay, it's not going to be 100% of the time, but most of the time it will do what you need. If you do start to build a package where you're using tidyverse functions, then you probably will need to dive into tidy eval a bit and get a little more comfortable with the idea of quoting and unquoting / evaluating arguments in their correct place. Okay, I have a challenge for you here. What I would like you to do is write a function that summarizes any numeric columns by returning the mean, standard deviation, min, and max. For bonus points, embed a meaningful error message. I don't know if you'll have time for that. And I'll probably do more like 5 minutes, not 7 minutes. But so here's an example, right, where I'm saying summarize calls diamonds is the data frame, and I want it to summarize the depth, the table, and the price. And so here I get depth, price, table. So they're in different order, but whatever. But I get the mean, standard deviation, min, and max. Okay, so see if you can write a function that does that. Okay, I'll give you 5 minutes. All right. Hopefully you made some progress, even if you weren't able to get the whole way through. I'll show you now the way that I approach this. The easiest way, I think, in this case is actually just to pass the dots. Okay, so we have data, and then we just say some variables. And then we just say data select some of those variables, whatever variables you give it, right? And then pivot longer everything, names to var, values to val, group by var, and then mean val, standard deviation val, min val, max val. That's it. Okay, so we're basically going to take whatever, basically you're saying, here's the data, and then whatever variables you want from that data frame, right? And then it's going to first select just the variables that you want from that data frame. And then it's going to move them longer so that it's there's only 2 columns. It's going to group by the 1 column, which is all the variables, and then it's going to compute those summary statistics of the other one. Okay, so then if I say for Palmer penguins, select if is dot numeric, and then summarize calls everything, there it is. Okay. Or I could, yeah, I'd say everything works. Does that make sense? Okay. We only have like 5 more minutes, so we probably won't get all the way through this, but I'll get a little ways into this, and then we can revisit it next class before we jump into the shiny stuff. So linearity. Let's say we wanted to see if an XY relationship was linear. So one variable that's a predictor and one variable that's our outcome. And we want to see if the relation between them looks like a straight line or not. Okay. So ideally, what we would do is have a function that produces a plot that shows what a straight line would look like, and then something that's less than a straight line that actually bends to the data more. Okay, and that way we could compare sort of this wiggly line that goes with the data with a straight line that we would maybe be assuming in some model that we're fitting. Optionally, maybe you have an additional argument to the function that optionally shows the data. So maybe, yes, it shows the data sometimes and not other times. And you probably want to set that with the default. Okay, so here's one way that we could maybe do this. We have this function check linear. I'm going to pass it the data as the first argument, whatever the x variable is, whatever the y variable is, and then I'm going to say by default I want the standard error to be true, and I want points, so the dots, right, to be false. Then I'm going to say, okay, p ggplot data xy, and then if points, then we're going to add geom point to the p. If the standard error, then we're going to say geom smooth method lm geom smooth. Okay, so these are the 2 smooths that we're adding to it. One with the linear model, so that's going to be the straight line, and then one without that, so that'll be the wiggly line. Okay, so this is if the standard error. If not, then we're going to say lm se equals false and se equals false here, and then it's going to return p. Okay, so that's what we might think would work, but it doesn't. Okay, why? Looking back here, why does this not work? Any ideas at all? Let's look back at this error message. Object bill length mm not found. Why is it not found?
It's looking in the global environment, the way it's written.
Exactly. So we have x and y here that it's feeding it, and those are just bare variable names. When I say bill length mm, it's looking inside the global environment for that thing to feed into the function, and it can't find it. Okay, so that doesn't work. So instead, we're going to do the same thing, basically, but I'm just going to wrap that x and y in those double curly braces. Okay, so that's all I have to do, and now it works. Okay, so check linear, penguins, bill length mm, bill depth mm, and it works. Okay, if we want to add points, we can say points equals true, and that's going to then make it go to the other side of it, right? And one of the things that's really nice about this is that because it's outputting a ggplot object, we can actually just add additional layers to that ggplot object. So we say check linear, here's our function, right? And then I'm just saying plus labs, right? That's a ggplot function to add labels, X, Y, title, subtitle. And then I'm adding a theme to it, theme dark, and it all just works, right? Because we're outputting a ggplot object, so we can add additional layers to that ggplot object. Okay, so let's stop there. We'll come back to this next time. We'll revisit these last 10 slides or so, and then we will move on from there to Shiny, which will be the topic for the next, I think, 3 lectures. There's one day in there that we have off because of a holiday. Oh, that's not till week 10. So yeah, we go Shiny 1, 2, 3, and then we have a sort of review day for functions and Shiny, and then we have a day off, and then we have the last day is intro to package development, and then your final project is due here. Okay, so again, I mentioned this last time, but your draft of your final project is due in 1 week from today, so you should have that there, and then we'll have peer review assigned that day as well. Okay, so it should be in a GitHub repo with your group at that point. Okay. Okay, thank you all. That's all I have for you today.